Hello, everyone. It is very nice to have the chance to attend this webinar. My name is Pengcheng Liu, and I am now conducting the research in the Technical University of Munich as the Humboldt Research Fellow. Today, my topic is about the regulation mechanisms of the electrochemical interfaces in metal batteries. My talk today has 3 sections. The first section, I will give you the brief introduction about this field. As we know, the lithium-ion battery is very important for our daily lives now. Also, the lithium-ion battery is super important for the roadmap of the carbon neutral. So 3 awesome scientists were awarded at the Nobel Prize to award their huge and great contributions for the invention and the development of the lithium-ion battery fields. In 2019, on the other hand, with the fast development of the electric vehicles, it further needs that the lithium-ion battery need to have the higher energy density. For example, many countries have proposed that the 400 watt-hour per kilograms at least will be the next target for the battery energy density. However, unfortunately, as for the current lithium-ion battery construction with the ceramic cathode and the graphite anode cannot further increase the energy density. So, fortunately, one of the most promising solutions and ideas is to develop the metal batteries with the metal anodes. For example, the lithium metal anodes has a 10 times higher capacity than the graphite. Also, the lithium metal anodes has the relative lowest potential, so that the lithium metal batteries has the highest output voltage. So the lithium metal batteries will have the ability to greatly improve and increase the energy density. However, the metal batteries also has a lot of the challenges and problems. The first problem is the growth of the dendrite. We can see the sharp dendrites, the sharp metal dendrites will punch through the separator and then cause the short circuit and the explosion. So the challenge is like the effective model to describe the electron deposition of the metal anodes. And the second problem is the low Coulombic efficiency, CE. The reason is that the metal anodes usually has very high reactive activity, so that when electrolyte contact with the metal anodes, a lot of the chemical and electrochemical side reactions will happen. So behind these challenge and problems, the key scientific issue and the problem is the regulation mechanism of the electrochemical interfaces in for metal anodes. After thinking carefully about the process of the electron deposition of the metal anodes, we found there are 2 very important electrochemical interfaces. The first interface is the interface between the metal anodes and the current collector. This interface has the dominant influence on dendrite growth. And the second electrochemical interface is the interface between the electrolyte and the metal anode. It is the solid electrolyte interface. It is the ICI. So the ICI has directly the influence on the Coulombic efficiency. So we can see if we want to construct effective the metal anodes, so we have to stabilize both of the electrochemical interfaces. So the first thing we tried to do is to stabilize interface between the metal anode and the substrate. First, we proposed a new model to describe the process of the deposition of the metal anodes. Also, through the new models, it was found effective method to suppress the growth of the dendrite is to increase the surface energy of the substrate. So in order to identify the model, we applied and used a self-assembly method to construct and fabricated a graphite oxide coated 3D copper. This kind of the current collector has the higher surface energy. In the molten metal experiment, we found, as for the functional current collector, the molten metal can quickly wet the whole surface of the functional current collector. However, as for the bare current collector, no matter how long it will take, the molten metal wetting can be found. Also, in the electrochemical metal deposition experiments, it also can be found. As for the functional current collector, the plated metals are very uniform. No obvious dendrite can be found. However, as for the bare current collector, we can find the obvious dendrite can be found at the beginning of the plating. So, in summary, in this work, we proposed a new model to describe in detail the progress of the deposition of the metal anodes. And also, through this model, we propose effective methods to suppress the growth of the dendrites through increasing the surface energy of the current collectors. Then the second thing we tried to do is to stabilize interface between electrolyte and the metal anodes. It is SEI. So first, we made the very careful thinking. Ions must transfer in the electrolyte. Also, the SEI forms through the reactions, the chemical and the electrochemical reactions when the electrolyte contacts with the substrate. So then we were thinking carefully, if we can improve the wettability of electrolyte, the electrolyte can quickly and fully and uniformly wet the whole surface of the substrate. Then maybe the formed SEI will also become more uniform. So light, then the plated metal maybe also become more uniform. So in order to identify our source, we have to fabricate a substrate with the which has the full wetting ability for the electrolyte. So then we applied the typical wetting theory, the Wenzhou model. Through this wetting ability Wenzhou model, it was found the wetting ability can be greatly improved through increasing the surface roughness. So then we fabricated aluminum powder coated aluminum foil substrate. Through the SEM image, we can clearly see This kind of the substrate has much improved and increased surface roughness. Then, in contrast, the control sample or the baseline sample is the flat aluminum foil. Through the electrolyte wetting experiment, it can be found the electrolyte, as for the substrate with the mass increased surface roughness, the electrolyte can quickly fully wet the whole surface of the substrate. And then it was found, it is very interesting. The formed initial SEI in the next step is also very uniform in the structure and the chemical components. Also, as for the following the metal plating, the plated metal is also very uniform. No obvious dendrite can be found. However, in contrast, as for the baseline, the flat aluminum foil, no matter how long it will take, no electrolyte wetting can be found. Then the next, the formed initial SEI is also not uniform. So like the following plated metals, we can see the obvious dendrite. So in this work, in summary, we propose a new method to stabilize the SEI and suppress the growth of the dendrite through increasing the electrolyte wetting ability on substrate. It is also the first time to fully review the important role of the electrolyte wettability for metal batteries. Then we also want to construct a full-cell metal batteries. So we have to consider another electrochemical interface in the side of the cathode. It is a cathode electrolyte interface. It is the CEI. So we were thinking whether we can propose a new effective method to synergetically stabilize both SEI and the CEI. And then we were also thinking carefully about that the ion transfer between the cathode and the anode must pass through the separator. So we were thinking whether we can regulate the ion transfer behavior through the separator modification. So for identify our source and answer our questions, we made a fantastic design. We used the hierarchical and higher surface energy aluminum fluoride to double coated the both sides on the common separator. The reason is that we plan to realize the full electrolyte wetting and also plan to regulate the ion transfer behavior by increasing the surface roughness and the surface energy. And then we also plan to realize the synergistic regulation for the both SEI and the CEI through the double coating. So in the electrolyte wetting experiments, it is found the electrolyte can quickly and fully wet the whole surface of the separator, the modified separator. However, as for the bare separator, no matter how long it will take, no the electrolyte wetting can be found. Also, it is very interesting. the modified separator can also improve the ion conductivity and the ion transfer numbers. So these data and the results fully reviewed. The modified separator can effectively and greatly improve and regulate the ion transfer behaviors. Then through the Creo SEM and the Fiber Amazing, as for the modified separator, the plated metal are very uniform. No the obvious dendrite can be found. However, as for the bare separator, we can see the obvious dendrite growth. Also, we further assembled all cell metal batteries by comparing a PB cathode. It is also found our modified separator can greatly improve the stability of the full cell cycling. Also, through the Creo SEM Amazing, the modified separator can effectively stabilize the cathode and effectively avoid the cracks of the cathode. Also can effectively avoid the crossover of the transition elements from the cathode materials. So in this work, we proposed a very effective method can realize the synergistic, the regulation and the stabilization for both SEM and CI. Then, because of the contribution for the fields of the metal batteries, we also received the invitation from the accounts and in detail described our proposed methods and the models and the series for the metal batteries. The last section, sorry, it is a little advertising. Now I am now serving as the guest editor for the Nanomaterial Science, which is published by the Elsevier. And now the immediate impact factor is up to 11, and it is expected the first impact factor this year can be over 12. Now we are all organizing the special issue about the carbon neutral. And now we have received many contributions from the many international reputation groups. For example, the group of the Professor John Goodenough. So now we still sincerely welcome more contributions, including original research, reviews, mini reviews, or perspectives. On the other hand, I'm also serving as the committee board for two international conferences. One is about the 3D printing, one is about the two-dimensional materials. We are also sincerely looking forward to meeting you at, in the two conferences. And then, thank you. That's all. Thank you so much.